and welcome back to another video. So last time we looked at how to calculate the energy change or enthalpy change based on bond enthalpies. So the amount of energy being put into a system and the amount of energy being released, and the difference between that is is delta H, or the enthalpy change. So today we're going to look at a more practical way of calculating enthalpy, or heat of the reaction, as we call it. So amount of energy that's changed by using a practical setup. So this is called calorimetry, and the application of this is to find out the amount of energy in food, for instance. So in the back of a packet, if you have energy content, chances are people in the lab somewhere has done this type of experiment to identify how much energy is in a specific food source. So if we look at it, the setup is, so we've got something like, imagine a peanut, and a peanut is just put on a little stand, and then we light the peanut up. Okay, so this peanut is going to start burning, and as it's burning, it's releasing energy. So bonds are broken and bonds are made, it's releasing energy, and we want to know how much energy is being released by this peanut that's burning. So what we do is we find something that will catch up, or will catch all this energy, and we put some water over it. Okay, so we fill a container with water, we put some water in it, and then we add a thermometer, and we just find out what the change in temperature is. So what's going to happen in an insulated environment and no energy is lost, all this energy will be going into the water. So if we can find out how much energy has gone into the water, we by default can find out how much energy has been lost by this peanut. And the calculation that we use to do this is called, I just call it MCAT, but it's Q equals MC delta T. Okay, all these stand for, so Q means the amount of heat that has been released or been absorbed by the water. The mass is the amount of water, because this amount of water will make a difference. If you think of warming up a swimming pool compared to a cup of coffee, the size of the container and the amount of water will make a difference of how much energy is needed to change the temperature. And then C is called the specific heat of a reaction. So we know water takes 4.18 kilojoules of energy to raise its temperature by 1 degree. So that's what we use. The specific heat capacity is a constant. We will give you that, C. And then delta T, delta means change, and T is the temperature. So the change in temperature of this reaction, or of this water. Okay, so let's have a look. If we burn this peanut, and the temperature changes from 30 degrees to 50 degrees. Okay, so at the start we had water at 30 degrees, we burnt the peanut under the water, and it ended up being 50 degrees. This mass of water, we'll say, is how many mils? We'll go 50 mils of water, and luckily we know 1 milliliter equals 1 gram of water. So if we have 50 mils of water, it's going to be 50 grams of H2O. That's in there. Okay, so let's pop this into the equation. Q is the amount of heat that got absorbed, or energy that got absorbed. The mass is the mass of water, so it's going to be 50. The specific heat capacity of water that we know, scientists know, is 4.18. And the change in temperature is going to be this difference in temperature. So if it got colder, if it was an endothermic reaction, this would be a negative number. But at the moment, because we're burning something, heat is being released. So we know it's positive, and the difference is 20. Let me get my calculator. 50 times 4.18 times 20. That will give you the amount of joules of energy that has been released. So this amount of energy, or of being absorbed, has been absorbed by the water. Because energy is measured in kilojoules, we convert this into kilojoules, so it's going to be 4.18 kilojoules of energy, right? And that tells us how much energy has gone into the water, which is great to start with. Okay, so we know that. Now we need to standardize it, because what we also know is that not all peanuts are the same size. So we need to get it into a standard value, and the way that we use the standard way of doing things in chemistry is by using moles. So we need to identify how many moles of peanut have we burnt to start with, and then we can take this amount and put it into relation to the amount of moles that was burnt. So imagine we have a peanut that weighs 2 grams, okay, and this molar mass of the peanut is 4 grams per mole. What we need to do now is find out the mole of this amount of the amount of mole for this peanut, and the calculation that we use is N equals little m over big M, molar mass. So we've got 2 grams divided by 4, and that's going to give you 0.4 mole. Right, so now we have the amount of mole, 0.5 mole. We have the amount of kilojoules that's been released or absorbed by the water. And what we're going to do now is we're going to find out what is the energy transfer in this whole system. So what we do is we take, so we've got this one and that one. So the next calculation that we'll be using is delta H equals minus Q over N. So delta H is the change in temperature. The Q is the thing that we've just worked out, this amount of energy, and the N is the mole. We put this as a negative because what we've calculated here is the amount of energy that went into the water. So if that's gone into the water, we need to do the opposite when we look at the peanut. If that one has been absorbed, the peanut will be released. Okay, and that is just doing the opposite of what we originally have done. So let's have a look. Q equals minus 4.18 divided by 0.5 equals divided by 0.5, and that will give you 8.36 kilojoules per mole. So in the enthalpy change, the difference in temperature, or the difference in energy in the system, whether to start and to end, is 8.36 kilojoules of mole. So let's quickly go back again. Calorimetry is the practical way of identifying how much energy has gone into or has been released by using water to absorb it. We use this calculation, Q equals MC delta T. M stands for the mass of the water. Don't worry about the mass of the peanut yet. So the mass of water, a constant that will be given to you, and the delta T is the change in temperature. So we're going to work out the amount of energy that's been absorbed by the water and change it into kilojoules. The next step is to identify the amount of moles that we're working with, that we originally burnt, and then after that we're going to use this amount of energy divided by the amount of moles, do the opposite, change the sign of it, and that will give you a number there that will tell you the enthalpy change. If we look at the negative, it means it's an exothermic reaction. Remember that video on exo and endo? So because it's a negative, it means it's an exothermic reaction that we can kind of justify because we've burned something. So we know this is going to be an exothermic. If this number was positive, we know that this solution, or the water solution, would have gotten colder, which means that this would have absorbed energy instead of releasing it. So I'm hoping that it's a quick summary of what the calculations that we use when we work out enthalpy change by using calorimetry. This is pretty much the practical way of doing it, instead of if you think of the bond enthalpy. But yeah, so it's pretty simple. Just make sure that you don't get tripped up by the mass of the water. So remember, it's the mass of the water, not the mass of the peanut. And the next thing to remember is to work out the moles and then change the sign of this equation when you work out the enthalpy change. So yeah, watch out for my next video. See ya.